Hi, I'm Heather, and today I'll be presenting Edema, an active compression device, which demonstrates how robotic textile can be utilized as a personalized and accessible solution to treat edema. As a brief introduction, edema is when excess buildup of fluid is captured within tissue without being drained. And edema is a pervasive condition that can manifest not only in upper and lower extremities, but also peripheral sites like hands and feet. In this research, we focus on people with peripheral edema in the hand in particular, where the swelling can be detrimental and chronic, which significantly compromises activities of daily living. So in response to that, we designed a system where a certain amount of pressure is exerted across the finger in a sequence to give mobility to the fluid. And while doing so, we created a wearable solution that is not only accessible and customizable, but also could potentially treat patients from their home. So if you look at current ways to treat hand edema, conventional regimens are limited with regard to portability and customizability of device and cost and time in the case of physical therapy. For instance, these pneumatic sleeves on the left, which are one of the most popular and common devices, come with tethered compressor. And despite the high pressure it can deliver, just because of the sheer size, it is difficult to compress small spaces on the hand. Manual massage in the middle is carried out by trained physical therapists, which could be extremely costly and puts a lot of strain on the therapist as well, because this practice is labor intensive. Isotoner or compression glove is basically a garment that's woven tightly to deliver around 32 millimeter mercury. Because of small pressure and prolonged intervention time, isotoner is considered more of a management tool than active treatment. So this is the gap we are trying to fill with KnitDema by providing something that's designed to fit patient's hand and something they can potentially take home. So with that motivation in our paper, we introduced robotic textile system that provides sequential compression, customization to individual hand, and programmable pressure levels. Also in our paper, we set up a mock system to simulate shunting of edema fluid as the pressure is being exerted. We identify pressure parameters and characterize them using the mock system to inform the final design of the device. And finally, we implement the device in an hour-long intervention and evaluate it in mixed method user study. Our paper builds up on 3 areas in the related works where we looked at current edema treatments in practice, robotic textile for medical applications, and co-design methodologies. What's really compounding edema's detrimental impact on daily activities is the conventional treatment, which I briefly covered. For instance, the pneumatic sleeves are tethered and cumbersome, preventing distributed pressure. And manual massage, again, is expensive and it requires patients to commit their time. And because massage treatment takes place in clinics, people with compromised mobility would have trouble accessing resources. And other less popular treatments include fluidotherapy, which utilize fine solid particles flying in a hot dry whirlpool to stimulate the hand, and taping, which stimulates edema flow through passive compression. And because of the nature of this work, where we're tackling a particular medical condition, we co-design not only the device, but also study protocol with rehab physicians and physical therapists over 1.5 years and across 3 institutions, where co-design process cover the full implementation of device and evaluation of device feasibility. And lastly, robotic textile is defined by its ability to deform its shape according to the actuators integrated into fabric. And here I'm sharing some of promising and relevant applications of robotic textiles, including exoskeletons, rehabilitation devices, and therapeutic garment for certain psychological conditions. KnitDema provides both passive and active compression through a needed substrate and actuators, and its pressure can be programmed through a portable printed circuit board. So if I break down the device, it has an active sleeve for the index finger, where shape memory actuators constrict the area from tip to the base, and the rest of the device is machine needed based on the measurement of individuals, which provides passive compression. And finally, you can program the actuation using the printed circuit board, which is enclosed with a battery. We considered knit structure desirable to deliver passive compression as it allows us to modify the shape of the device, create hollow channels for actuators, and can have the loop structure interlaced more tightly lengthwise while giving more stretch laterally through the specific structure. The factors that determine passive compression are yarn properties and knit structure, loop length, which is how tight each loop is, and lastly, how well the device fits to the measurements. On the other hand, elements that affect active compression include properties of shape memory alloy, in what sequence the compression is moving, the orientation of SMA bands, mechanical parameters of compression, which I'm going to elaborate on later. And here I lay out how we identify compression parameters and how we characterize them utilizing a mock system, which reacts to external pressure in a very similar way an extremely swollen finger would do. Here is the setup of the mock system, where we created a finger with porous foam saturated with water and silicone encapsulating the foam, and we gave a resistance on the outlet, which then is connected to the burette. And the parameters that we wanted to empirically characterize were band intervals, sequence intervals, duration of each compression, and lastly, SMA number within a sequence. We conducted a factorial test for band interval, meaning the unloading period of SMA between compressions, and sequence interval, the unloading of SMA between sequences, while actuating 3 SMAs for 30 seconds. We found out that applying pressure continuously without any intervals or breaks resulted the best. And the next parameter to characterize was duration, where we compressed the mock finger without any breaks, but by varying the duration of compression. And we noticed that actuating SMA for 105 seconds drained more than the others. Lastly, we were interested to see how many SMA would shunt the greatest amount of water. We realized when we activated 6 SMA bands, it was able to move 9% of water, which was more than the others. So we based the final design of the device on the findings from this characterization. So after we fabricated the device based on the results, we implemented them in human subject user study. The protocol of the study included pre-study survey where we asked patients demographic info and hand measurements. And based off of that, we customized devices. Then on the day of intervention, we measured baseline and have the patient wear the device for an hour and collected the measurements again. This was followed by a post-study survey. Then we ended the study with interviews. Volumeter was used to measure the volume of water overflowing as patients submerged their fingers. And next, we measure circumferences of 3 points, first, second joints, and the base. And lastly, for range of motion, we measure the inner angle between 2 motions where patients straighten their fingers and flex fingers to maximum. We analyzed the data through a linear mixed signal model, and our model informed no significant changes before and after the intervention. But from the descriptive data, 3 out of 5 showed decrease in the finger volume, and on average, people lost 2% in volume. Similar to volume analysis, our model showed no significant changes in the range of motion. But from descriptive data, participants on average showed a decrease of 1.7% in the flexion angle, meaning their fingers became more flexible, which was deemed favorable. And while the circumferences of the 3 joints were significantly different, we failed to observe significant changes here. But overall, the base showed a decrease of 1.46% on average. And from the interview responses, what was notable with regard to wearability was that patients were highlighting how light and comfortable the device was. And as for the sensation or sensory stimulation of the device, patients perceived other tactile sensation than compression. And they also expressed different sensitivity between bony versus fleshy areas of the finger. And as they compare the device to their standard therapy, people brought up how silent and compact the device was while operating, and also highlighted how the device fit to the hand. And when we asked how the patient viewed the device as remote treatment, they seemed to favor the portability and then the fact that they can program the pressure as they see fit. While we're primarily looking at the feasibility of the device, our user study left us insights we can reflect on for the future work. First is improving the efficacy. We could take anthropometric body landmark as design parameters. We could make measurements more rigorous. We could extend the intervention. And our future work could also expand the device to the full hand, where we could study if there is backflow of fluid between the palm and the fingers, improve portability, and lastly, enable more accessible programming of the PCB for clinicians. And as for evaluation, we could observe ebb and flow of edema and identify pain points through long-term study, evaluate adherence of the device, and we could also see different methodology for in the wild user studies. So that's all for my presentation, and thank you for listening.